Welcome to the Margin Call, where market mechanics meet strategy.
Forensic accountants have a strange trick for catching fraud. They don't read a single word of the financial statement. They just look at which digit shows up first in every number, and somehow that's often enough to catch someone lying. It sounds like nonsense. A number is a number. The first digit should be random, except it isn't. And once you learn why, you'll start noticing this pattern everywhere, in stock prices, in river lengths, in your own bank statement. This is Benford's Law. Here's an experiment. Pull up any large, real-world list of numbers, the population of every country on Earth, the length of every major river, the closing price of every stock on the NASDAQ. Look only at the first digit of each number. Ignore everything else. You'd expect each digit, 1 through 9, to show up about equally often, 1 time in 9. That's what random should look like. It's not what happens. Digit 1 shows up as the leading digit around 30% of the time. Digit 9 shows up less than 5% of the time. And this holds true across wildly unrelated data sets that have nothing to do with each other. Something is going on underneath the numbers themselves. This pattern has a name, Benford's Law. It was first noticed in the 1880s by an astronomer who realized the first pages of a shared book of logarithm tables were far more worn and dog-eared than the last pages, meaning people were looking up numbers that started with 1 far more often than numbers that started with 9. Decades later, a physicist tested it properly. Over 20,000 real numbers, pulled from newspapers, sports statistics, physics constants, addresses. The pattern held every time. The formula is almost embarrassingly simple. The probability that a number starts with digit d is log base 10 of 1 plus 1 over d. Plug in 1, you get roughly 30%. Plug in 9, you get under 5%. No randomness. No coincidence. A precise, predictable curve. Here's the intuition, and it's cleaner than it sounds. Imagine a number that's growing, a stock price, a population, a bacteria, colony, anything that grows by compounding, multiplying, not just adding. To go from a leading digit of 1 to a leading digit of 2, say, from 100. Let's actually check it. Take the market capitalization of every company. On a major stock exchange, thousands of companies, wildly different sizes, nothing coordinated about them. Sort every single one by its leading digit and count them up. The bars land almost exactly where Benford's Law predicts. Digit 1, the tallest bar, just like the formula says. Digit 9, barely a sliver. This isn't cherry-picked. Run the same test on city populations, on the numbers in a company's utility bills, on the digits in a tax return. The same curve shows up again and again. Here's where it gets useful. Benford's Law only holds for numbers that occur naturally, through real growth, real measurement, real transactions. Humans are terrible at faking that pattern. When someone invents numbers, a fabricated expense report, a cooked set of books, they tend to spread their digits out evenly, because that's what random intuitively feels like to us. But real numbers were never evenly spread to begin with. So fabricated, data doesn't blend in. It stands out as unnaturally flat in a place where the real thing should curve steeply downward. The fraud doesn't announce itself. The shape of the distribution does. This is exactly what forensic accountants do with it. In the early 1990s, an accounting researcher formalized digit analysis into an actual auditing tool. Run it on a company's expense reports, its accounts payable, its reported revenue by division. If the leading digits drift far enough from the expected curve, that dataset gets flagged for a closer, human look. It isn't limited to accounting, either. Tax authorities use it to prioritize which returns to audit. Auditors use it to sanity check financial statements before deeper review. It's cheap, it's fast, and it works on any dataset large enough to test. Before this feels like magic, some real limits. Benford's law doesn't apply to every kind of number. It needs data that spans multiple orders of magnitude and grows or is generated in a roughly multiplicative way. Assign numbers, phone numbers, ID numbers, ages, zip codes don't follow it because they were never generated by any growth process. It's also not proof of anything. A dataset that fails a Benford test is a flag for further investigation, not a guilty verdict. And a dataset that fits the curve isn't automatically clean. A careful fraudster who's studied Benford's law can fake the digit pattern too. It's a first-pass filter, a smoke detector, not a conviction. Auditors don't stop at the first digit, either. There's a second digit test, a first two-digit test, even tests on the last digit for signs of rounding. Each one has its own predicted curve, and each one catches a slightly different kind of manipulation. Some of this now runs automatically, scanning millions of transactions in seconds, flagging the tiny fraction that deserve a human's attention. The underlying idea never changes. Real growth leaves a fingerprint. Faking it convincingly is much harder than it looks. Step back, and this is bigger than fraud detection. Anything that grows by compounding, your investment portfolio, a company's revenue, a viral trend, the number of cells in your body, carries this same invisible signature. The numbers you deal with every day were never as random as they felt. They were shaped, quietly, by the mathematics of how things grow. The next time someone hands you a spreadsheet, remember, even the first digit has something to say. That's the strange, hidden math behind the numbers everyone trusts and rarely checks.